In tonight's edition, recorded for radio, four noted scientists take part in a panel discussion on the fundamental essence of information and how it applies to some of the most complex questions in modern physics.
Good evening, ladies and gentlemen. Welcome to Perimeter Institute's public event series. My name is John Matlock. I'm the director of the Institute. It's my pleasure to welcome you here and to all of the audiences who are tuning us in around the world electronically. We have a very special presentation on the physics of information. We have a special format, a special host. He is Bob MacDonald of Quirks and Quarks. Bob is one of Canada's best-known science journalists. He's not only been the host of Quirks since 1992, he has an extensive history in communicating science. This includes his broadcasts on CBC Radio Ideas, As It Happens, and Morningside. On CBC Television, Bob was the host of the children's program Wonderstruck, and we continue to see him on The National, where he is the national science correspondent. In addition to his work with CBC, TV Ontario, and other broadcasters, Bob has written for the Globe and Mail and has written several popular books. He's received several honors for his contributions in science communication, including having received the Michael Smith Award for Science Promotion from NSERC, the Stanford Fleming Medal from the Royal Canadian Institute, and the McNeil Medal for the Public Awareness of Science program from the Royal Society of Canada. He also holds a number of honorary degrees from Laurentian, the University of Guelph, and Carleton. Ladies and gentlemen, please welcome to Perimeter Institute's stage, Bob MacDonald.
Ladies and gentlemen, wow. I'm Bob MacDonald, host of Quirks and Quarks, our national science program on CBC Radio. Perhaps you've heard of it. I'd like to welcome you to this very special Perimeter Institute presentation. This evening's discussion is called The Physics of Information, What the Universe Doesn't Want You to Know. And let me begin by introducing our very distinguished panel. On my far left, Dr. Chris Fuchs, a long-term visitor at Perimeter Institute who specializes in quantum information and quantum foundations, and he's also an adjunct professor of physics at the University of New Mexico. Next to him, Dr. Tony Leggett is a professor of physics at the University of Illinois and the 2003 Nobel laureate in physics for his work on superfluidity. He also is a member of Perimeter Institute's Scientific Advisory Committee, and more recently he was named the Mike and Ophelia Lazaridis Distinguished Research Chair at the University of Waterloo. On my right, your left, Dr. Seth Lloyd, a quantum computer engineer and a professor of mechanical engineering at the Massachusetts Institute of Technology, and Dr. Leonard Susskind, a professor of physics at Stanford University and associate faculty member at Perimeter Institute. Ladies and gentlemen, this is your panel for this evening. Now, if you've attended other Perimeter Institute events like this, or occasionally listen to Quirks and Quarks, you know something that most people have figured out. Physicists are not like the rest of us. I know, they look like normal human beings, but they don't see the world the same way that we do. Take information, for example. When you or I have a question, what do? We look it up. You go to a book, you go to the internet, you ask somebody, the information is just data that's out there, all you have to do is find it, or maybe share it with someone else. But that's not how physicists view information. They want to know what the information itself is actually made of. So imagine you're looking up information on a website. Now to you or I, we just see the details that are on the screen. But suppose you could look inside your computer with a really powerful microscope. Now you see the actual bits of data moving through the wires and the circuit boards. They're individual kernels of information. And these bits are being manipulated. And they're being transferred here and there as tiny little electric charges. Or you can look at an apple. Not the kind you type on, but the kind you eat. You might take a bite out of that apple. And you'll see a bite. But a physicist sees a bit. Or millions of bits. And those bits define the apple. Its shape, its color, its texture, its very existence can be defined as bits of information. So this idea that information and physics are intimately related has involved some of the world's greatest scientists in long-running intellectual debates. And their ideas on the physicality of information provide deep, though controversial, insights into some of the hardest problems in modern physics, including our understanding of the universe, one of the smaller problems we have, black holes, and paradoxes that you find in quantum mechanics. Their research is also leading to new technologies to calculate, to store, to transmit information in quantum computing, quantum cryptography, and quantum teleportation. Beam me up, Scotty. So let's get down to the nitty-gritty and see what information we can glean from our guest today. And I'd like to start with Dr. Seth Lloyd from MIT. Now, most of us see information as something that you just read or you copy or you share with somebody else. What's that got to do with physics?
Well, everything. Sorry, do you want a longer answer?
A little longer. This isn't the news. Sorry.
Ludwig Boltzmann in Vienna, Josiah Willard Gibbs at Yale, they actually discovered the fundamental formula that described information. And they didn't describe it in terms of bits. They discovered that formula because they were looking at how atoms move around. And they wanted to quantify this funky stuff called entropy. Now, entropy was at that time known as a quantity that gummed up the works of heat engines, of steam engines, and kept them from doing the amount of work you'd want them to do. But phrased in modern terms, what Maxwell, Boltzmann, and Gibbs discovered was that entropy is actually information. It's bits. So these atoms, as they move around, they carry bits of information with them. And every time two atoms collide, those bits flip. So in fact, not only does information have everything to do with physics, but physicists actually discovered it to begin with.
And it could also be what, now we have light that's carrying information, like fiber optics, so it could be a quantity of light as well.
Yeah, so if you want to see, if we're looking at how the information processing revolution came about, it's because scientists and engineers figured, oh, everything's already got this information associated with it, let's use it. You know, a particle of light, a photon, it can have a bit of information, like if it's wiggling back and forth like this. So if I take, my Ray-Bans, I put it like this, photon wiggling back and forth like that, you can call that a 0. Photon wiggling back and forth like this, Ray-Bans like that, you can call it a 1. So all these, particles, physical entities have information associated with them. And when we build things like quantum computers, all we're doing is just taking advantage of that.
So does that mean, then, that information is limited by the laws of physics?
Darn tootin'.
Another precise answer there.
Wow.
Let me turn to Chris Fuchs from Perimeter Institute. Can you give me an example of how the laws of physics allow us to do things with information?
Oh, well, I certainly can. But I think, actually, just to follow up on Seth first,
okay.
I've got to tell you about the first time I saw Seth Lloyd in public. He was emphasizing at that time not that everything can carry information, but that everything can be used to compute. And to make this dramatic, I remember him pulling off his shoe and putting it on the overhead projector and saying, you could even use this old shoe to compute. So when he says these things, he's serious about it.
So what was your question? Well, I guess an example, a little beyond the shoe, of how you could use the laws of physics to manipulate information. And do new things with it.
Well, you can certainly do new things when one takes into account quantum mechanics. So how shall I say? Here's a lovely example, something called quantum cryptography. The task that's set in front of two people, Alice and Bob, is that they'd like to share a secret. They'd like to communicate to each other privately. In the classical world, where there was no connection, at least no seen connection between physics and information, when they would send messages back and forth between each other, somebody could gather information and it has no effect on the carriers of the information. Well, in the quantum world, there seems to be a deep connection between the properties of things and the information that one can get about them. So, for instance, if you get information about something, it changes the system in the process. This leaves a trace. Alice and Bob can see this trace and they can learn whether someone has listened in on their conversations. So that's one example.
Okay. Now, Dr. Susskind, how do you define information?
Well, I think I would call information everything that you need to know about a system to know what happens next. So, for example, if you had a bathtub full of hot water, what information do you need to know in order to know whether to get into that bathtub or not? Well, you need to know its temperature, you may need to know its volume, to know if there's enough water there, and so forth. But that's a very limited amount of information. There's an enormous amount of information stored in the position and velocity of every single molecule in the water. If you really want to know exactly what's going to happen next, you need to know the position and velocity of every single molecule in that water. So there's an enormous amount of hidden information that you don't ordinarily see when you look at the bathtub full of water. That hidden information, the information that you can't see, is what's called entropy. And if you really want to know in detail what will happen next from any given initial starting point, you need to know all of the information, which means everything that can be known, all the numbers, all the velocities, all the positions, which are the maximum amount that you can ever know about that bathtub full of water. And if you knew it, you could predict what will happen next. That's what I call information.
Now, how close are we? I mean, that sounds to me like a huge amount of information. How close are we to actually knowing that? Just in a bathtub full of water.
Well, usually when I get into the bathtub, I know the temperature and the volume, and that's about it.
So the physics doesn't seem to be playing a lot.
Right. There's an enormous amount of hidden information that you can't see, and it goes under the name of entropy.
But I want a definition here, the difference between what we think of as classic physics and quantum physics.
Yes. I think in principle it really is the same thing, but I'm afraid that to give you the sharp distinctions between classical and quantum, I would have to give you a course in quantum mechanics.
We don't have time.
No, we don't have time for that. So I would suggest that you come to my evening course, which we call Quantum Mechanics for Old People. And about as many people here come once a week to find out what quantum mechanics is. It's also on the internet.
Okay, but in general terms, as I understand it, in classical physics, you're talking about gross motions, like Newton's laws, push something in action, reaction. With quantum, I think of the very small, what's going on within the atom, within the very tiny world where things don't behave the way they do out here.
Yeah, the character of quantum information is a little bit different than the character of classical information. It's a little more coarse-grained. In some sense, it's not quite as detailed. The uncertainty principle prevents you from knowing all the things that one would think one could know classically. So it takes a little bit less information in a certain sense to know what a quantum state is doing. On the other hand, it again corresponds to knowing the enormous amount of microscopic information that's in that bathtub full of water.
Okay. Let's bring Tony Leggett from University of Illinois into this discussion. How do you define information?
I think fairly similarly to what Dr. Susskind has done. As far as I'm concerned, information always has to be about something, and it has to be